Hello. Now let us see an example of finding voltage difference or a voltage across a device in a circuit in ways that we will explore in more detail and in more complicated circuits later on. So here is a very typical device, a very typical circuit rather, is excited by a particular voltage source that I have indicated here as VS1. This can easily be assumed right now in your minds as a battery because it is providing a constant voltage difference. Notice the polarity of this voltage difference. The plus sign is up, the negative sign is down. Later on, we'll learn more options for voltage sources as well. We are given that this VS1 value is equal to 10 volts. So I'm going to write it here. We're also given that VD is 0 volts. This is something that we covered a little bit in the theory. But as a reminder, typically the very bottom node of a circuit is assumed to be ground. In other words, is assumed to be equal to 0 volts. It doesn't have to be, but this is a very typical assumption. And finally, we're also given that VB, the voltage at node B, is equal to 8 volts. Now, the first thing I would like to notify you about is again the fact that even though we're using the same symbols to indicate a potential difference, we're using V for that, and also to indicate an absolute potential, we're using V for that again, it is truly important that you understand what the symbols mean. VS1 is a potential difference or a voltage difference. It refers to voltage at point A minus voltage at point D. The VB is the value that refers to the voltage of node B, the absolute potential of voltage at node B. So I'm saying this, and I'm spending quite a bit of time right now early on in the course, but later on I will be using the words voltage and voltage difference without being too careful about them, because that's really what happens in real life, and you will need to understand the meaning of those words from the context. Let me also say one more thing that we will see later on in more detail, but it's confusing quite a few students in the very beginning. And that is that the red node that I put down here is the same thing as the green node that I'm having right here, is the same thing as this blue node that I'm right down here. And in fact, all of these nodes have been called D. Now you may say, but isn't this node here different than this node here and different than this node here? The answer is electrically they're equivalent. What does that mean? It means that the electric potential, the electric voltage of these nodes is the same. It's 0 volts here, is 0 volts here, and 0 volts here. Another way to say the same thing is that the physical length of these ideal wires is irrelevant in circuit calculations. When we talk about an ideal wire, we essentially mean that you can move freely a charge from this point to this point without having to spend any energy. An ideal wire, in other words, is assumed to have zero resistance. Resistance is a concept we'll define later on. But the important thing to realize here is that when you're moving charges in an ideal wire, you spend no energy, which means that the voltage difference is zero. Zero voltage difference between here and here means zero energy difference. Electrically, they are equivalent. So the same thing, of course, you can say by looking at this node here with this node here, the voltage is the same. It's 0 volts here, it's 0 volts here, it's 0 volts here, and so on and so forth. So do not get confused that somehow things are changing. It doesn't matter how physically I draw the circuit. What really matters is the electrical potential of the nodes. All right, with these nodes, now let's go to our example. We have to find a few potential differences and a few absolute potentials. So first we have to find the potential difference VAD. So let's look at that. Node A is here. Node D is here, which of course is the same as we just discussed here. So really, I can write down that VAD, the voltage difference between nodes A and D, is nothing else but VS1. is basically the potential difference across the nodes of the voltage source Vs1. And therefore, as we already know, this is equal to 10 volts. Now, if somebody had asked me what is the value of VDA, then the answer would have been very similar, except that, of course, VDA, which is equal to VD minus VA, is the negative of VA minus VD, and therefore this is negative VAD, or of course negative 10 volts. So I hope this gives you a good idea of how to find this potential difference. Now let's proceed with VA. So VA, which is the absolute voltage at node A, is nothing else but the difference Vs1 minus plus, of course, the VD, which is going to be, of course, 0, and that means that VA is 10 volts. So clearly, the VA is nothing else but Vs1 volts above VD, and since VD is equal to 0, this is equal to 10 volts. Now, the next question is to find out what is VAB, the voltage difference between node A and node B. And notice what I just did in the circuit. I wrote VAB here, and I put plus on this, negative on node B, because that's what we mean when we write VAB. So VAB is VA minus VB. VA, we have already found that is 10 volts. VB is given as 8 volts, and therefore the result of this potential difference is 2. And finally, we need to find the voltage difference VBD, which is the voltage difference here. This is VBD. And of course, VBD is going to be equal to VB minus VD. And this is equal to 8 volts minus 0, or simply 8 volts. So clearly, there is no challenge here in terms of algebra. But I hope you'll go back and you will revisit the solution. You will be able to repeat it yourself and be convinced that you truly understand when we're talking about a potential difference, when we're talking about absolute potentials, and then do the same calculations. So thank you. We will see you next time.